did we talk about last time? Well, let's cheat and look. All right, so last time we did Coulomb friction, talked about, how that's discontinuous, et cetera, and how that's hard to simulate. Then we talked about the maximum dissipation principle, which was this optimization formulation that captures the stick-slip Coulomb friction behavior. And this is where you get this idea of a friction cone. And this optimization problem turns out to be a second-order cone program, which is a nice convex problem that we know how to solve really well. So that's cool. And then we talked about a bunch of sort of more or less standard simplifying assumptions or approximations that are made to this setup. Linearizing contact manifold, aka sign distance function, turning the friction cone into a pyramid, using Euler integration, et cetera, that turn this thing into a linear complementarity problem, or LCP. And that those are really closely related to QPs, but in general, they can be non-convex QPs, right? And these are pretty standard. There's good solvers for these. There's solvers that are really closely related to interior point methods, basically interior point methods. More or less, it's just the interior point method for a QP, but sort of tweaked for this setting that you can use to solve these. Other methods, these have been widely studied. So the whole game is you get this thing to look like an LCP, then you use a stock LCP solver. And this is what Bullet, Dart, Gazebo mostly do. And it's super standard stuff. So that's kind of how a lot of these simulators that you have maybe used before kind of work under the hood. Anything else to say about that? I don't think so. But yeah, there again, there's approximations to make it an LCP, right? So this is the source of some of these weirdo artifacts that you will see, right? Even these hard contact things like Bullet, because they're linearizing the sign distance function and stuff like this, you do still get a little bit of interpenetration. And often because of that linearization, you have to run them at really, really high sample rates to get realistic behavior. So it's pretty normal to run these things at like a couple kilohertz. And if you go much slower than that, you start to see really bizarre behavior with things like doing weird sinking into the ground stuff and all kinds of other weird badness. So any questions about that? So I think you're basically, at least at a high level, up to speed on like how modern robotic simulators work from a physics perspective. So we're going to start talking about now for like the next couple of weeks, basically to finish off the courses. So that's all the physics. What we're going to talk about now is sort of some of the more algorithmic aspects of how these things work under the hood. So we're going to start talking about kinematic chains and like structure of multi-link systems, aka robots with lots of links and joints, how to set those things up when you have lots of degrees of freedom, and then how we solve those things efficiently, right? So in all these things, we've got these optimization problems to solve, whether it's an LCP or even just inverting a mass matrix to get, Q double dot in the manipulator equation. All these sort of end up having somewhere you have to solve linear system. You have to do a Newton solve in an implicit integrator. You have to invert a mass matrix. You need to deal with constraint Jacobians, et cetera. So in general, for large, complicated robots, this can be expensive. And there's been a lot of work in the last, 40-ish years on trying to make these algorithms efficient. So we're going to talk about, hopefully, if I don't screw up the scheduling and take too long, we'll get to like the kind of famous linear time algorithms, Featherstone, RNEA, this kind of stuff that you maybe have heard of that there's no physics in there. It's pure, those are algorithmic ideas, right? So what we've talked about so far, you can set up and solve anything you want, right? But it's not necessarily fast. So we're going to talk about how to make these things fast, run real time, et cetera, and like some of the tricks that get played that exploit the structure of these problems to handle large, complicated, many degree of freedom robotic systems. That's what we're getting into now. So yeah, but I'd like to kind of draw the line between physics versus algorithms, right? Cool. All right. Any questions about anything? Projects, homework, this stuff, last time, anything, life in general? Okay, cool. Let's do it. So today, probably some of this stuff is going to be review if you're a robotics person or more mechanical person, and you've maybe taken KDC and stuff like this. Today, we're going to start real easy with this stuff. We're going to talk about fixed base manipulators. And that's basically a fancy way of saying like very classical robot arms, like industrial arms that are bolted to a world frame, and have a bunch of links. And we're going to sort of talk about the kinematics of these things So forward kinematics. And then we're going to start talking about dynamics of floating-based systems with quaternions, which is a thing that's going to take some time and effort. Still kind of wrestling with how to do that, like how to explain that the best way, because it's kind of gnarly. So we're going to start getting to that. The end of today, we'll start getting into that. We'll definitely like go into next time with that stuff, but hopefully we'll get to the meat of that by the end of the week. Okay, so as far as the homework goes, again, please try the homework this week. There's a problem in there that's about contact stuff, which you should mostly be able to do now. There's a problem in there that's this like inverted pendulum shake the bottom thing. It's in 2D. We're going to do and I ask you to do kinematic stuff and write down the mass matrix and stuff like that. We're going to do that stuff today. So you should absolutely be able to do that first problem, the like, what is it called? What did I call that problem? There's a politically incorrect name for that problem that's archaic and now I can't remember. Anyway, that. You can do that problem after today for sure. And you should be able to do most of the other one. And we'll get to the rest of that this week. So give it a shot. Anyway, okay. Fixed base manipulators. So classic stuff that you've definitely seen if you've done robotics, you know, KDC stuff before. These are sometimes called serial or open chain systems. And these are really like the prototypical example are industrial robot arms. Which, you know, most of the stuff on these things is figured out between like, I don't know, the 60s and the 80s. And there's like, you know, big literature. It's pretty much a solved problem. Yeah. So open chain, we will talk about this. It basically means that if you start like going down the links of the robot, there's no self intersections where it sort of connects back on itself. That would be called a closed loop system. There's no physics in there. So this is like a thing that people talk about a lot. You maybe heard of like, who's heard of like, you know, closed kinematic loops versus like open kinematic chains, right? Okay. So everyone's heard of this. What, can anyone tell me like why those are a thing? Like what makes them interesting or hard, or why are people scared of them? You have any thoughts on that?
Because they keep going no matter what happens.
Can you?
Like they don't have feedback. So if someone walks in the way, the robot arm can.
Oh no! Okay, so we're talking about different things here. So I think you mean open loop, as in a control problem. We're not talking about that. We're talking about the topology of a robot. So how, like the mechanical topology. So maybe anyone else heard of this before? Want to give us a, yeah. Yeah, so maybe, it depends how you look at these things. So yeah, basically like you can think of does everyone know what a 4-bar mechanism is? That's like a prototypical closed loop system, right? So you've got like 4 links and they're closed like this. And the idea here is that like there's, okay, so you could sit there and pick out like and how many degrees of freedom does that thing have? A planar 4-bar? That's like a good question. It depends. Yeah, so if one of the joints is pinned, it has 1 degree of freedom, right? But it has a bunch of links. So I could pick some angle and write down the dynamics in terms of that one angle, right? There's nothing weird about this. There's no physical weirdness. The reason these are a thing is that there's many algorithms, fast algorithms for doing this kind of stuff, for doing robot dynamics, that depend on not having any of these closed loops to work. Specifically, the classic, like fast linear time algorithms, Featherstone's algorithm, recursive Newton-Euler, which we'll talk about a little bit. They assume that things are serial or open chain and don't have any closed loops. There's topological like math reasons that that you need that. So what people end up doing By the way, if you write down the dynamics by hand, there's no issue with a closed loop whatsoever. You pick some coordinates, you write them down, everything's good, no problem. The problem comes if you try to use a stock dynamics package that uses Featherstone's algorithm, RNEA, one of these standard algorithms that assume an open chain. When you do that, the hack to make it work is you unroll the loop to write down the dynamic, to write it down in these packages, and then you add on a constraint after the fact to bolt the loop back together. So if you want to simulate a 4-bar with like Majoko, one of these things, you end up having to do this. You have to unroll the loop, write the dynamics down as if it were a serial chain, then add a constraint on outside of the dynamics, like the main, dynamics stuff, the RNA stuff, to pin it back together, which is annoying. So that's what's going on there. And we'll talk a little bit more when we get into these like fast algorithms, why that is a thing and why it happens. It's not too hard to like see where that comes from. Yeah, I guess that was a long diverging sort of discussion on what these are. Okay, so let's draw one of these things. So we'll start in 2D. So let's say we got like X, Y, theta. And let's say we've got like, our ground, whatever. And we've got a robot arm that's got a bunch of joints. So we have like a joint that bolts it to the ground. We have a link, we have a joint, we have a link, we have a joint, something like this, right? And then maybe we've got some end effector-y thing, whatever. It can branch, right? So we can have something like this, like a gripper. That's totally fine. No problem there, right? Okay, so let's see, what should we draw on here? So we've got center of mass of these things, which we'll use, and we've got joints. And these are, so those are joints, these are links. And this is sort of the terminology. Okay. And a closed loop, right, would be if I say took this, and like bolted it back on over here, right, and made a joint like that, then it would be a closed loop mechanism, right? So this is serial chain, open chain, whatever you want to call it, not closed loop. Closed loop's not allowed for now. But again, if you write it by hand, no big deal. It's fine. There's nothing weird about the physics. It's purely like an artifact of these algorithms that are popular that sort of critically depend on this assumption. Okay, so we'll write that down. For now, we won't allow any joints that form closed loops. So yeah, the loop thing is really like this topological. You can imagine if you made a graph of the mechanism, if that graph like did that, right, then we'd have problems. Okay, so so here's what we're going to do now. So we've got all these links, so we got all these joints. It turns out, right, for systems like this, we can easily compute the position and orientation, aka pose, of every single link, right, at its center of mass, given the joint angles. That's what we're going to do. That's called computing the forward kinematics, right? What's going on up there? So in the world frame, from the joint angles. And this is called forward kinematics. Okay, who's done this before? Everybody's done this before, just about, yeah. So this is like baby robotic stuff, but we're gonna do it. We're gonna belabor this a little bit today. This is only gonna be a little bit of today, just to make sure notation and all that is on the same page. So in 2D, this is really easy. we're going to start with, say, so I'll go with the picture here, right? So we'll start with, and these are all kind of the joint angles we're going to call Q's, because that's the standard notation. And we'll start with the orientation of link 1. So this is theta 1 is just going to equal Q1, the first. So let's make some. So that's easy. And then what we want to do next is compute the position of the center mass of that guy, right? So we're going to write that down. So that's going to be R. And it's basically just going to be some rotation matrix stuff, which we'll write down real quick. This is a 2D rotation matrix, right? And we're going to define some stuff. So this guy is going to be called R of theta. And this guy is the vector from the first joint of link 1 to the center of mass. So I guess we should call this A1. So to be clear, this is in the body frame. So what I'm doing here is I have like these little vectors that tell me where the CG is on the link relative to the joint. And I rotate this into the world frame and basically tack it on to the last kind of position I was at, right? So I start at the joint. I say, here's the vector in the body frame from that joint on the body to the CG of the body. I'm going to rotate out into the world frame. There you go. And then I'm just going to keep doing this, right? I'm tacking these on link by link. Yep.
For the rotation matrix, the negative sign plus the under.
Did I screw up? Totally possible. Okay, let me think about this for a second. Sine, oh, it depends on our coordinates. What did I do? It also depends how I define my angles. So did I define it up from the, yeah, and that, so if theta equals 0, yeah, and then, wait, if theta is positive that way, I pick up a little bit of y component, right?
Wait, is theta 0 like arm horizontal?
According to this little picture up here, it's defined this way. Did I do that right?
Yeah, so if you have a little theta,
Then I get positive.
yeah, and
Y.
Y would be the lower left entry or
Yeah, I think you're right. Yeah, good call. I think that's, let me think about this for one more second. It also depends on how we define the body frame, right? But I think we'll go with, that's making some sense to me. Be careful and check. I'm okay with this. I think we'll go with this today. Cool. Okay, cool. Basically, this guy rotates us from the link frame to the world frame. We just keep adding these things on as we go in the world frame, right? Okay. And this is link center of mass position. In the world frame. And then we basically just kind of keep doing this from the base to the end of the arm, right? So this sort of thing. So we have theta k equals theta k minus 1 plus qk. We add the joint angles as we go, and then rk equals rk minus 1 plus rk minus 1. I'm going to define these in 1 second. So this is the one we just did. So A is the vector from the joint to the center mass. B is the vector from the center mass to the next joint on that same link, right? And I'll draw a picture of this in a sec. So let's draw a little picture just to make sure we're all good on this. So link. I need to draw this bigger so I can write all the stuff. Link, center mass, joint. So this is the A. Say AK, and then this is B. Okay. We have an X joint. And same thing over here. To be like, you know, the next A and B, and then the joint angles are defined sort of in this world frame. So we did it like this, right? So this would be theta K minus 1, and then in this kind of like world frame situation, this would be theta K, and then QK is if I were to like compute some relative angle between the neighboring links, right? This is QK. Okay, does that make sense, everybody? You guys have all done this before. This is easy, hopefully. Okay, cool. So what I'm going to do now is I'm going to just like write this down in 3D, which is hopefully, if this makes sense and all the definitions make sense, it's a trivial generalization to 3D. All that's happening really is that we're going from just these angles, theta K, in the world frame to represent the attitude of the link to rotation matrices that represent like the global orientation, right? That's it. Everything else is the same. So let's just write that down real quick. And hopefully it makes sense. So we're going to write, I'm going to start like using a bunch of decorations for these things. So this is the rotation from the link 1 body frame to the inertial frame, right? Body to inertials always helps probably write down the attitude. And this is going to be this gets a little trickier, right? Because now, before I could just add the angles. In 3D, I can rotate in different directions, right? So this guy is unique to each link or each joint type on each link, right? And then encodes what that actual joint is doing, like which way it's rotating, et cetera. So I'd have to write this guy down. Notice this is S1 of, you know, it's gonna be S sub K for each link, right? To encode which way the joint goes, basically. Does that make sense, everybody? So you got to write that down for each link, each joint. And then position is the same. This stuff's the same. We do this deal. And then the sort of difference here is now instead of adding angles, we've got to multiply rotation matrices. And I'm going to slightly simplify notation. It's basically, if I bootstrap here at time step 1, right? I have these SKs defined for every joint. And then I basically take this guy and just multiply it on to the previous attitude of the previous link, right? So this is the 3D version of adding angles, right? It's in 3D, so I got to multiply rotation matrices. That's all that's going on. And then the rest of this is basically the same, though. So here's the position stuff, looks exactly the same. Just the sort of rotation matrix version. Everyone cool with this? Any questions about this? It's just that you can rotate in different directions now and stuff. So these guys look a little different. Okay, cool. So right now we're going to focus on the 2D version and sort of start digging into like how you compute dynamic stuff. And then once we're kind of through this, we'll do the 3D version, which is going to get nasty because it's going to involve differentiating quaternions and stuff, which we'll talk a little bit about. Okay. Okay, so let's write down the kinematics, this thing, right? This like little routine we just wrote down. Let's write this down as a function. Okay, so we're going to define this function. It's going to take in the q's, so the vector of joint angles, and then it's going to spit out the center mass position and attitude of every single link, right? It's going to just do this forward kinematics routine. So the output is this. In 3D, those thetas would just be replaced by rotation matrices, right? All Rn theta n. Cool. So that's what we get out, and that's what we put in, right? And this guy is the n joint angles, right? Cool. So we'll call this little guy, we'll call this little k, this like nonlinear function, takes the q's in, spits out the positions and orientations. From this guy, I can, so this is going to give me those positions. From this guy, I can easily compute also the velocities in the inertial frame of each link, right? So we're going to do that right now. That's super easy. So linear and angular velocity. So this is what you expect. You just chain rule this guy. So we take ddt of this thing. And so this is just partial k, partial q times q dot, right? And then this thing, this partial k, partial q, this is going to show up a lot. So we're going to give this thing its own letter. We'll call this, usually people write this as capital J for Jacobian in a lot of contexts. That gets too confusing because there's too many Jacobians we have to keep track of in here. And it's also, we use J for the mass matrix for rigid body because I is identity matrix. This is very annoying. It's too many notational things to keep track of. So we're going to use little k for kinematics and then big K for the kinematic Jacobian. So we'll call this guy big K of Q. And this is, what's the dimension of this guy? It's not square. So it's the output, remember, is, so here the output is size 3n, right? In general, in 3D, it would be 6n, right? For like linear velocity, angular velocity. So this guy in 2D is 3n by n. And we call this the kinematic Jacobian. This gets used a lot, and I'll show you how to do the 3D version a little bit. Again, annoying quaternion derivative stuff. That's why we're doing the 2D version first to hopefully get some intuition. Okay, so cool. So this gets me all the reason we do this, the primary reason we do this is this gets me the inertial frame velocities of this guy, which is what I need to compute kinetic energy. So now we're going to look at how you compute kinetic energy. So if we have the mass and inertia of each link, we can compute kinetic energy. Here's what that looks like. So this guy, remember, for each link in, at least in 2D, it's just kind of the 1/2 mv squared stuff. So it's going to be mk r dot k transpose r dot k. That's the linear part. And then the angular part is jk, which is a scalar in this case, times theta dot k squared. Right, so remember, these guys are 2D vectors. So we got to take the dot product of those guys to get b squared here. This is a scalar in 2D, so that's easy. Theta dot squared. These guys are both scalars in this case, right? In the 3D case, this is going to become a matrix, and we're getting omega and stuff. Gets a little more complicated. Okay, so this thing, we can write this as a big matrix expression, like so. So we've got all the I have all this stuff. I can sort of squish a big mass matrix in here. This looks like M1 I J1 dot 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 dot. Then like MN I JN. And then a bunch of zeros. So this is a big block diagonal matrix, right? And then same stuff over here. So we got the R dot 1, theta dot 1 dot dot dot. r dot n, theta dot n. Cool. So we're going to call this guy, this big block diagonal thing that just has the scalar mass and inertias along the block diagonal for each link. We're going to call this M bar. There's other names for this. I would call this the maximal coordinate mass matrix or inertia tensor, whatever you want. The important thing to note here is this M bar for any system is always constant, right? Not a function of any kind of joint angles or anything, right? It just collects all the mass properties in a big block diagonal matrix. Okay, so the mass, here's where the mass matrix that we usually talk about in robotics comes from. We take this guy. Remember, these guys I can get with that kinematic Jacobian from the Q's, right? So I write this down just using the kinematic Jacobian and the Q's. I get the following thing. Right, that looks good, everybody. I just replaced this thing with KQ dot, right, that we just derived. And now this thing in the middle, which is basically just the M bar smushed by the kinematic Jacobians. This is the standard M of Q that you're used to in joint space in robotics, right? So we write this guy as 1/2 Q dot M of Q dot. So the important thing, right, is like, you know, the mass properties of these things doesn't change, right? That's a constant. All this like M of Q stuff, all that is coming from the kinematic Jacobians here. That's it, right? And if you ever want to get this in general, you can do it like this. You write down the kinematics, diff them, get the Jacobian, write down all the masses and inertias of all the links, and you just compute this like matrix sandwich thing, right? Yeah. Yeah, so it takes in this guy, right? This is the joint angles. So there's n, if there's n joints, this is n dimensional. If there's n joints and n lengths, this is n dimensional. This guy, for each link, I have a 2D position and a 1D theta. So there's 3 of these, like in 2D, the pose of each link, I need 3 numbers, right? So this is 3n, this is n. So this guy's 3n by n, right? Takes in an n, spits out a 3n thing. Cool. And that sort of also jives with this, right? So this guy, again, each of these blocks for each link is 3n by 3n, right? Mass inertia. And then this guy basically smooshes it down to the joint space, which is n by n. But now the sort of like expense of doing this is I went from this nice constant thing to this like weirdo nonlinear, you know, metric thing that's a function of the joint angles, right? But this is the thing we're used to using in generalized coordinates, right? Has anyone seen this like this? No. Okay. What do they teach you in KDC? Huh? How do they get this though? I don't understand. But how do you like get this M of Q if you're given a robot? Oh, that's dumb. Okay. Anyway, it's really simple. Hopefully this makes sense. You just need the kinematics and then the mass properties of all the links, and you smush it all together, right? Does that make sense? And like another way to think about this, right? You can think about this M bar guy being in like the ambient, like Euclidean space, right? Of the whole thing. And this guy is like, you can think of this as just projecting this into joint space, right? That's how you like do a projection of a matrix. Okay, cool. Hopefully that makes sense. Yay. Maybe that was useful or insightful. I don't know. Okay, so yeah, basically same story. We're not going to do it explicitly right here, but if you wanted to do the dynamics of this thing, right? Mass matrix, that's one ingredient. The other stuff you need, right, is the potential energy, right? You can do it very, very similarly. Yeah. So like if I wanted to compute the gravitational potential of this thing, right, all I would have to do is forward kinematics and then compute like mg height, right, for each link. I can use the forward kinematics to do that too, right? And that's easy, and I can use all the same tooling to do it. So we won't. So you can get the potential and then the Lagrangian, right? Any questions about that? It's like super straightforward from here, right? This is kind of the main meat. Okay, so now we're going to do that in some code. Yeah, let's look at that. Where is code? Code is here. Okay, cool. I think things are going to work. Here we go. We're going to go back. So we'll do a slightly more fun example this time, which is not a single pendulum, but a double pendulum, which is the cartoon serial chain thing with 2 links, right? It's like the simplest multi-link thing I could think of. Okay, so here's the forward kinematics function. I wrote this down by hand, but like taking a quick look at it, here's what's going on, right? So this is the X component. I think I should have drawn the diagram. This is the standard kind of way we write this down, where it's hanging down, and that's 0, 0. And then the first angle is defined relative to hanging down. So it's different from the picture I drew where I did it relative to sideways, but hopefully that's not too terrible. Okay, so X component, Y component, and then theta, right, of the first joint. In terms of the lengths, these are basically those A's and B's, right? And then the next one, same kind of deal. This is this is the Y component of the first link. And then like, oh no, this is X, Y theta first link. This is X, Y theta for second link, right? And that's just like this, the stuff we just wrote down. I just wrote it by hand. Okay, cool. Here we're going to do the potential energy. This is just gravity. It's like what you said. I'm going to evaluate the kinematics. Then I'm going to pull out the Y components from the kinematics. And I'm going to do MGY. Cool, easy enough. Kinetic energy. We're going to do exactly what we just did. I'm going to take the kinematic Jacobian. So I'm using forward diff to get this because I'm lazy. But I wrote down the kinematics. I diff it with respect to Q. I get this guy, right? Now here's my world space, you know, or whatever, inertial frame velocity, right? KQ dot. That gives me that vector that's got the R dot theta dot, right, of all these guys. And then I'm going to dump that into my standard kind of like the big version, right? So this is M bar, MMJ, blah, blah, blah for each link, 1/2 MV squared kind of thing, right? That's the big one, right? I computed it like this instead of smushing the matrix, whatever. Okay, cool. Lagrangian, kinetic minus potential energy, easy as it gets. I'm going to now compute, I'm going to write down the Euler-Lagrange equation now. I'm going to use forward diff to compute everything. So again, lazy. So these are the first and second derivatives of these guys, right, with respect to. So this is dl dq dot d squared l dq dot squared. What's that? You want to tell me what that is? It's the second derivative of Lagrangian with respect to q dot. What do we think that is? Where does q dot show up in the Lagrangian? Yeah, I think so. So yes, but I think you're overthinking that. Yeah. So where does q dot show up? It's in the kinetic energy, and it shows up as like 1/2 q dot transpose m q dot. Right. So if I take 2 derivatives of that, what do I get? It's just the mass matrix. So this is actually the, if you write down a weirdo Lagrangian in any kind of weirdo coordinates, and you want to know what the mass matrix is, and you didn't explicitly compute it or whatever, and you wrote down this big expression for a Lagrangian, the mass matrix is the Hessian of the Lagrangian with respect to the q dots. That's what it is. Maybe that makes sense. I don't know. That's what it is. But that's makes sense, right? It's always q dot transpose m q dot, right? That kind of thing. So if you do that, you get the mass matrix. Fun. And this guy, we didn't really talk about this maybe yet. This is the mixed partial, right? So this is like dq dot dq. And we know what that is. Thoughts? In terms of like your manipulator equation terms, that kind of stuff. It's not exactly, this is basically the Coriolis term. It's basically the C in the manipulator equation. Okay, cool. Fun facts. Okay, so here's my forced Euler-Lagrange stuff. This is again the mass matrix, right? So this is doing M inverse. And then what's the first derivative with respect to Q? Basically your potential term. And then this is the weirdo Coriolis stuff that we talked about. And then I'm also going to tack on torques at the joints in here, which we didn't really talk about yet, but we will. Okay, cool. So this is zero Lagrange. This is basically the manipulator equation. If I call this M and this G and this C, right, this manipulator equation, right? That's what those things are. I don't know if we did that explicitly yet. We will. Sorry, I didn't yet. Okay, for fun, because why not? I'm going to throw a controller in here with so I'm gonna assume I have torques on both joints. Oh. All right. Torques on the joints, controller, cool. I'm gonna simulate this now with no control from random initial conditions. We'll watch what happens. If you've ever done anything with double pendula, you kind of know what's gonna happen, right? This is the famous chaotic double pendulum thing. We didn't really talk about it too much, but who's seen a double pendulum before? Heard of this whole chaos thing? I have one of these actually. I have a good one that's got like really nice bearings. So it's like low friction. So it actually does the chaos thing. The only problem is you have to bolt it on to something really sturdy to make it work. It's kind of a pain, but I could totally bring that in. I feel like I could probably bolt that to something in here. It needs like a really solid base to bolt onto to actually work. This is also really painfully slow. Here we go. Okay, yeah. So this basically looks like total insane garbage. If I did this again from slightly different random initial conditions, hopefully it'll go faster. Yeah, like insane random garbage. You can use this as a random noise generator. That's fun because it's, yeah, chaos, etc. Okay, so what I'm going to do now is, so two links, right, hanging down. I basically randomly initialize them and they go nuts and like flip all over the place and whatever, chaos. What I'm going to do now is turn on, just because, I don't know, I have joint torques now, right? And I'm going to put in torques. I'm going to just do PD control, where the proportional stuff is set for the upward equilibrium. So the first angle is pi, the second angle is 0, right? So relative angles. So this should stabilize me up at the top. And again, it's fully actuated, so this is easy, right? So that makes sense, right? And the damping, the D term takes care of damping it out. So now this just like goes boing, pegs up there, right? Cool. Okay. I think that's good for now. Any questions about this when we're trying anything? Double pendulum, easy, cool. Okay, fun. Rope trick. That's what that's called. Okay. So let's see. What should we say about this? Okay, so things about this. So we did this in sort of joint space, right? We wrote everything in terms of joint angles, dynamics in terms of joint angles. Unsurprisingly, if you do that, handling torques on the joints is easy. Because those are your coordinates. I just stuck the tau in there on the end, right? And that's nice. So joint torques are easy, which is one of the reasons they're like used in these, you know, serial chain manipulator things, industrial arm things. But if I want to deal with anything other than joint torques, it's a little more complicated. We're going to do that now. So if I, for example, if I wanted to have a force on the end effector, right? Not the same as a joint torque, not in joint space, right, et cetera. So we got to do some extra stuff. So let's do that next. Okay, so how do we do this? So I know you guys have seen some version of this before. We'll do it like the legit way. So we can get this whole story about how I apply external forces. How do we get forces into the like Euler-Lagrange situation before we did this, right? At some point, I think we did. Did we? Now my brain is not good. Virtual work. This sort of, so we did this in here, I'm pretty sure. We talked about forced variational integrators, right? Yes, not insane. I did this, I talked about this. Okay, so how do we do forcing in those like variational integrator things? This thing called like D'Alembert's principle, or the Lagrange D'Alembert thing, which is, I would argue, kind of a hack. But what you do is, so we're going to do that again. So remember what that was. I'm going to write it real quick. So it's basically like, you know, so remember our kind of like Euler-Lagrange, or our least action thing was this. So there's the action thing, least action thing. And remember, we basically tack on a term with the forcing in it. And the whole idea is basically that so when we did this before, this was the Q coordinates, right? And this thing, the whole idea is I take DDQ of this whole thing to get the dynamics. I tack on the second term. I just made this term up such that when I take its derivative with respect to Q, I get the F. And that's sort of like reverse engineered out, gets you the Euler-Lagrange equation with the F on the right-hand side. That's all I'm doing, right? Basically, I just integrate both sides of the Euler-Lagrange equation. So this, though, is actually kind of useful. Before I did this with Q, now I stuck this other guy in here. The idea this is some other coordinate, right? So this could be world frame coordinates, any coordinates you want. We're going to call them Y for bookkeeping purposes. So I'll write that in here. Okay, so whatever coordinates you want, world coordinates, anything. Okay, so the idea here is all I have to do to make this all work, I have to take DDQ of this whole thing, right? And set the derivative equal to 0. So I'm just going to do that. And when I get to here, all I do is chain rule this guy. So I take dy dq times delta q. And then that dy dq is the magic sort of thing that I need to map these things. That ends up being a Jacobian. So the idea here is that if I when I wrote down my dynamics of my tubing pendulum thing, I used joint coordinates, right? I used Q's for the joints. Let's say I want to go push on the end effector now. I'm living in the sort of world frame now, and I'm pushing on the end of this thing with some force vector. That's written down in world coordinates, right? I'm not basically anything other than torques at the joints doesn't naturally fit into this joint coordinate thing, right? I'm now standing outside the robot, pushing on it somewhere, anywhere I want, right? That's sort of in the world frame, right? So that's the idea. So to make this work, I want to write this guy down in the world frame coordinates, right? Some force vector in the world frame poking at this thing somewhere, right? And so I have some other set of coordinates that I'm writing that force vector down in that isn't the joint coordinates, right? So I can write that down however I want. Those are those other coordinates, right? Yeah. And then now when I go take derivative with respect to Q of this both thing, I chain rule through the Y coordinates to get to the Q coordinates, right? To get DDQ. So I'll write that down right now. And then that's it. That's all you got to do. And whatever's left there, multiplying the delta Q is the forcing term on the right-hand side. And all I did was pick up a new Jacobian, right? That maps those forces. So that's how you get that Jacobian end effector thingy that shows up to map end effector forces into joint space or whatever. So we got this guy that we're used to, that we've done several times now. Well, the Lagrange equation shows up in here, right? If I do the integration by parts tricks. And then this is, I got a delta Q here. And then if I do it on the other term, I get F transpose partial Y partial Q times delta Q. So the whole game, remember, is I want to write all this stuff. This same here is here. I massage this till I get it in terms of delta Q, and I try to pull the delta Q out, right? That's the whole game. And I do the same thing here. I massage this till I can pull out a delta Q. And in this case, it just means it's Jacobian. Here I had to do weird integration by parts tricks to pull out the delta Q, right? To get rid of the Q dot terms. Here I just chain rule through this guy till I can pull out the delta Q. Now, the argument, right? The classic calculus of variations argument is that this has to hold true for any delta Q. So now I just get this whole thing, right? Has to equal 0. So that's where we get it. And it looks like this. My brain is maybe not working fully today, so I'm going to ask you guys. So So Euler-Lagrange, did we talk about, I think we did, but I might be, did I talk about how to get from Euler-Lagrange to this manipulator equation? We did, right? I just did it again, but I saw lots of confusion, so I'm like now questioning myself. I'm confused. I can't remember, what I did, but yeah, so this is the Hessian of this guy, right? And it's sort of coming from this term, right? You get cool. This guy is this Coriolis term, comes from some weird mass matrix derivatives that we just saw. It's that mixed partial term, gravity terms, right? So it's just partial potential respect to Q. And then this is the external forcing term. This is the Jacobian that maps us from whatever weirdo coordinates, outside the robot we choose into joint space. And then this is the, force in whatever weirdo outside in the world coordinates we liked. Cool. Everyone cool with this? That's how you get this. You've seen this before, I'm assuming, right? Manipulate equation with this, so say end effector force, whatever you like. It can be anything though, right? It's super general. Okay, let's do that real quick. Okay, so now here's what we're going to do. We're going to apply a force in the x direction at the bottom of the last link. So it's in the world frame, and it's at the end effector, if you like, right? The end of the second link of the pendulum. That make sense? So here's how we do it. So I want to write this down. Remember, it's in the x direction in the world frame. What I have to do to get this, so what this is the x coordinate of the end of the last link. So I do the forward kinematics down the chain, and I get to the position of the end of the chain, and I take the x coordinate of that, right? That's it. That's what that thing is. And this is I guess this is the center mass of that second chain, whatever. It's the CG of the second link. So this is part of the forward kinematics that I just basically pulled out, right, to get me to the point where I'm applying the force in the right direction. I take its Jacobian, and that's the y that we just talked about. Now what I'm going to do is some dynamics-y stuff again. And in this case, we're going to put some damping on the joints. And then what I'm going to do is apply some force. So what I'm basically, if you think about this intuitively, I'm basically yanking the double pendulum to the right with some. So I'll start with a small force, and let's look what happens. Cool. So I started it hanging down, right? I'm yanking it, and it kind of like ends up, with gravity and stuff. It's sort of like in this equilibrium, kind of like this, right? So what should happen if I jack this force up really high? Eventually, it should just like peg all the way to the right, like basically like pi over 2, right? Let's see what happens. So I'll jack that up by a factor of 10. So it's kind of starting to do that, right? And if I jack it up really big, there you go, right? So now it's just pinned with the first make it pi over 2, and it's just straight out, right? So that checks out, intuitively makes sense. Cool. Any questions about that? That's that. End effectors, forward kinematics, Jacobians, blah, blah, blah. This is, I used y there because it's a different Jacobian, right? It's a different kinematics thing than the full robot, which we call K, different Jacobian, right? It can be like it's computed using kinematics-y things, right? But it could be arbitrary points, arbitrary directions. You get the idea. Okay, cool. All good on that? Cool. Okay, back to this. So double pendulum. With external force. So that was sort of cartoony, but hopefully you get the idea. This works in 3D, etc. Okay, so basically the note now we're gonna start talking about the 3D stuff. Okay. And we're going to have to revisit our friends, the quaternions. I guess I will preface this with, there are many, many ways to do this. You don't have to use quaternions at all if you don't want to. If you can use rotation matrices, right? And if you're a sadist, you can use Euler angles. Don't recommend. But so no matter how you do this, you're going to end up in a situation where you have to like compute these, basically the recipe, the stuff you need to be able to compute the forward kinematics of this thing in 3D to get, which is going to involve 3D rotations, right? Like you got to figure out the pose of these things in 3D. So you need some 3D rotation representation that you can kind of chain along the robot. That's thing number one. And thing number two is I need to compute velocities of this thing, right? So I need, and when I say velocities in the 3D rotation case, I mean omega. I mean the angular velocity that we are used to, right? So in order to do that, I have to find some way to diff the kinematics, which has this rotation representation, and somehow chain rule it through to omega, right? The unfortunate, like the root of most of these annoyances is the fact that there's no coordinate representation that actually corresponds to omega, right? I can't like integrate omega from a gyro into anything meaningful without doing some weird stuff. It has to be, you know, so Euler angles or quaternions or rotation matrices, no matter what, none of those things corresponds to the integral of omega, right? We kind of talked about this very early in the class with this whole thing. So like, that's kind of the heart of this thing. Like, so I can choose any rotation representation I want. That's fine to write the kinematics down. But then when I have to go to the chain rule through the kinematics to get my velocities to plug into, you know, 1/2 omega transpose j omega, I need to get the omegas somehow out of that rotation representation, which is always non-trivial, right? So I'm going to show you how to do this with quaternions, because that's what I like to use. And that's actually standard in like most computer graphics, simulation, aerospace, robotics stuff. We generally use quaternions, so not that weird. This treatment is maybe somewhat non-standard and somewhat, you know, Zach, but I think it makes sense to me. Hopefully it makes sense to you too. Enough caveats, let's do it. So you might have to like go back in your brain a couple of months to when we talked about this the first time a little bit. I'm going to try to ease us into it. So the key things, really this whole idea of differentiating with respect to, or you know, with quaternions. This is where all the annoying stuff shows up. We're going to try to make it as less, you know, much less annoying. Okay, so geometrically, we talked about this. I think we did talk about this early on, right? So geometrically, these quaternion things are 4D and they have a unit norm constraint. So they live on this sphere in R4. We call it the 3 sphere. So there's that whole thing. Unit sphere in R4. And then, so let's draw the terrible picture. So unfortunately, again, referring back to annoying notational overloading and how there's too many letters to keep track of. We used to use lowercase q for quaternions at the beginning of the class, but now we're using lowercase q for joint angles. Apologies. These are in fact the standard notations in the literature, but now we have a collision. We have to do something different. So I'm going to start using uppercase q for quaternions and lowercase q for joint angles. Please forgive me. I didn't think about this 2 months ago in advance enough to like deconflict these at the beginning. So hopefully you can like live with this. I'm sorry. So we're going to use, for now on, I guess, we'll use capital R for rotation matrix, capital Q for quaternion, little q for joint angles. This is what people do. There's 300 years of history here. I can't like do too much about it. Okay, so this is our Q. And then the key idea, right, is that the derivatives don't live on the sphere or whatever. They're not unit quaternions. Instead, they live in this like tangent plane situation, right? If I imagine taking the derivative of this guy, I get this like tangent plane over here. And my Q dot sort of lives in this plane, right? And sort of sticks off the sphere maybe. So we talked about this before, like this is kind of the space where omega lives, right? Is this tangent space kind of thing. So let's write that down. And this tangent plane is 3D. And this is sort of the idea is like omega. Omega is a 3D vector, right? So no matter what weirdo representation we use, that could be, you know, 3x3 matrices or 4D unit vectors, whatever. When I take a derivative, that derivative lives in this 3D tangent space. somehow. And I can always kind of do some weird thing to map that back into some 3D omega vector thing. And in particular, for quaternions, we talked a lot about this, and it looks like the following thing, where that's the quaternion product and this hat thing means to stick the 3D omega vector in as the vector part of the quaternion, right? And then we also talked about all this weird notation that I made up, where we are going to define a left multiply. Damn it, it's going to be a problem. Capital Q. So we define this left multiplication matrix like operator, right? That's equivalent to that quaternion product. And then we define also this hat matrix operator thing that takes a 3D omega. And basically it's a row of zeros and then an identity block, right? So this guy maps us into this guy, and this L of Q guy is equivalent to this left multiplication by the quaternion, right? So this sort of encodes the quaternion multiplication as a matrix. This is convenient because now I can just use normal matrix math to diff this and stuff, right? That's why we do that. Okay, cool. Everyone cool with this? We kind of vaguely remember doing this, hopefully. I think I do. It's challenging. Okay,
Sorry,
so
just an equal sign. It's Q dot equals 1/2 Q omega.
oh yeah, sorry. Thanks. Okay, good.
And for the like posterity of reading the notes, there's a little Q in the sentence above that I think should be a big Q.
Thank you. This is
Yeah.
definitely gonna be a problem.
No worries.
Thanks. All right. I'll try to like scrub the notes at the end and like on more sleeve, maybe. Okay, so what I want to do here, right, is I want to take this expression that maybe involves, you know, whatever 4D things. If I have some function f of q, and I want to write down, ultimately, I want to get a 3D gradient of that thing. That's what we're doing. And we're going to play some tricks to do that. Big Q. That's right. Doing capital Q. Almost did that again. Okay. So yeah, here's f of q. This we're gonna for right now we'll do gradient. So this guy's a function from quaternion to just a scalar, say. So big H, weird blackboard H is quaternions, Hamilton. Cool. Okay, so this is a scalar valued function of a quaternion, and we want to get a gradient of it. So the trick is we're going to basically go in here and say, we're going to use the quaternion composition, like the multiplication, right? These things don't add. So we're going to take a little tiny rotation by some little delta Q delta. We're going to write down a phi, right? That little differential rotation thing. We're going to multiply it onto this Q, and we're going to kind of expand this out and use these tricks to get it down to a 3D gradient. So here's what we're going to do. We're going to parameterize this. With an axis angle vector. You could choose anything. You could choose Euler angles if you wanted to, any 3D representation. We're going to use axis angle vectors because they actually do, for small rotations, basically to first order in a Taylor expansion, they correspond to like an omega times a delta t. So this is like the closest thing you can get to like integrating omega, right? They actually do legit correspond to omega times delta t if you're rotating about a single axis. But if you're tumbling, they don't. And here we go. Okay, so we'll call this guy phi. And we're gonna, so small rotation delta q. If I write this down exactly in terms of the axis angle, we talked about this a while ago, right? So this is cos. Oh yeah, that, next to that, that's an H. That's supposed to be blackboard bold H. Like the same way you write R for real numbers. I'm just really bad at this. So that's what you, the set of quaternions, that's the sort of, so you know, like real numbers are R, complex are C, quaternions are H, like blackboard bold H.
And I've seen like S3.
No. S3 refers to the unit 3 sphere.
Oh, okay.
Like the geometric object, right? This refers to like algebraically the quaternions, and then the H is for Hamilton, who invented them. That's where that comes from historically. But yeah, that's like the quaternion equivalent of like R, C, etc. And roughly speaking, you think about these as like a generalization of complex numbers. There's actually this thing called the Cayley construction that lets you build these things out of pairs of, so it turns out this Cayley construction thing, which is kind of fun, aside, if you want to Wikipedia this sometime, you can create complex numbers. It basically is this bootstrapping like hierarchy where you can build complex numbers from pairs of reals, quaternions from pairs of complex numbers. And then you can actually keep going and you can build these things called the octonions from pairs of quaternions. It's kind of a weird thing, but it lets you like bootstrap these weird higher things. Aside, probably ignore that. Yeah.
So is H all quaternions or unit?
All quaternions. Yeah.
We're trying to get all.
Yeah, we're really trying to diff unit quaternions in here. We're not going to care about. So in general, quaternions can encode more. They can encode 3D transformations. They can encode both rotations and sort of like stretching as well. So if they're non-unit norm, that encodes like a uniform stretch as well as the rotation. We just want rotation, so that's why we can find them to be unit norm. But yeah, they in general can do other things. But we're not going to worry about that right now. Okay, cool. So this, hopefully remember this. I'm going to call this, what am I going to call this? We'll call this phi over 2. And then down here, we're going to get this like phi over norm phi thing. So that's the unit vector direction, the axis of rotation, times sine phi over 2. Do we remember this? This is the basically like the Euler identity for quaternions, and it's like how I map axis angles into unit quaternions. It's always unit norm, right? The sine cosine stuff, we talked about that. And this is also the quaternion exponential. The other fun fact about this, right? It's related to the Euler identity for complex numbers, like the e to the I theta thing. It's basically that. Okay, cool. So if I take this and I Taylor expand it for small phi, as in small angle approximation, approximate the sine and cosine, I get this thing. Cos becomes 1. And the thing on the bottom just becomes 1/2 phi. Does everyone see that? Cool. Okay. And so now I can then take that and turn that into, it's the identity quaternion plus this guy. AKA, this is phi hat, right? It's 1/2 phi hat. That makes sense. Okay, cool. So that's like the small angle approximation trick for the special case of quaternions and axis angles, small phi, blah, blah, blah. Now we're just going to plug this into F and do a Taylor expansion thing. Okay, so what we're after, right, is something like F plus delta F. Yeah. So I'm going to go in here, I'm going to take Q quaternion multiply by delta Q. I'm going to go plug this thing in and say this is approximately F of Q times my little approximate, 1/2 phi small rotation thing. This is equal to Q plus, if I plug in this guy, right? It's Q times that. So it's Q plus Q, this is a plus, times 1/2 phi hat. I don't see that. Identity plus the phi hat guy, right? So the identity gets me this guy, and then that's this Q times this term still, right? Cool. Okay, so keep going. I can now do some approximating. So I'm now going to just take this guy, Taylor expand, assuming this term is small, right? I'm going to Taylor expand F. So I'm going to get the original F of Q plus partial f partial q, which is just the regular Jacobian of f, treating like q as a normal 4D vector, right? Not as a quaternion. And then I'm going to sort of chain rule it with that guy. So this is L of q left multiplied by this q times this guy. And specifically, I'm going to expand it like this. So I got the h, and then I've got the 1/2 phi. Cool. So aside here, all right, one more thing. Okay, so then this means that the delta f, so f plus delta f, right? This is the original thing. I'm going to knock this off and just take the delta. And then this is what this looks like. L of q h, put the 1/2 up here. And then this thing, because it shows up all the time, we're going to give this a name. We're going to call this G of Q. And then this we're going to call the attitude Jacobian.
Sorry, isn't G of Q just L of Q times H?
Yeah, sorry. It is this guy, not the function's Jacobian. Okay, cool, thanks. So thing to sort of like note here, and then so finally, what I'm kind of really did there, right, is I basically like just plugged in the axis angle thing and then chain ruled through the axis angle mapping to, you know, quaternion mapping. But at the end of the day, like I get this kind of thing, partial f, partial phi, right, is in this case, I got 1/2 partial f, partial q times g of q. So that's like the thing I wanted, right? And so the message is basically I take the Jacobian of the function as if it were just a normal vector, and I slap on this attitude Jacobian thing. There is this extra factor of 2 floating around, as is very common in all quaternion things. This is the same factor of 2 that shows up in the kinematics up here, right? So note on this. So this is good. This corresponds to like omegas, which is ultimately what we're after, right? This is kind of why I did it. This particular choice of tiny rotation, because it maps into omegas nicely. And I get the same factor of 1/2 kind of thing floating around. Cautionary note or whatever. I did this. It turns out that this attitude Jacobian thing is like a real, like kind of basic thing that shows up. If I were to choose, say, a little Euler angle perturbation or anything else here instead of axis angles, this G shows up exactly the same. It turns out the G is like a general thing for any representation. What will change if I change to, say, Euler angles or whatever is this 1/2 factor. This guy depends on the choice of representation. This guy does not. This guy shows up no matter which one you use. And it's sort of a basic like Lie group thing. Okay. Any questions about this? So the idea here, what we're kind of going for is like a general recipe for taking any function and just like diffing it with respect to a quaternion, right? So any function I want, all I got to do is take its normal Jacobian and slap this extra attitude Jacobian thing on there, and maybe a factor of 1/2 or 2 somewhere or something like this, which you'll have to be a little careful about. Okay, that's the message. So take standard derivative, whatever Jacobian gradient, and then right multiply. Big Q. That's it. Okay, cool. So that's hopefully easy. And maybe you need a factor of 2 somewhere. Be careful. So the last thing I wanted to do, which yeah, I think we can do real quick before we leave, is we also in here are going to need to do this on the output side. So if we have a function that like eats a quaternion, spits out another quaternion, or eats some other set of coordinates and spits out a quaternion, where's that going to show up for us? spits out a quaternion. That's the forward kinematics, right? So it takes in joint angles and then spits out pose for every length. So so this one that we just did eats quaternions and spits out something else. We need eats joint angles, spits out quaternions. So we actually have to basically do the same trick, but on the output side of the function rather than the input side. The punchline is not surprising. Basically, I'm going to get a G transpose on the left instead of a G on the right. Deriving it is a little bit of work. We'll do it real quick. I think we can do this before we have to go. Okay, so here's what we do. So here we say we've got Q is equals f of x, where, this guy can be sort of Rn to quaternion. It's a little better H. Okay, so here's how we're going to do this. So the output, under some kind of small perturbation, we'll call that Q prime. And remember, these guys multiply. That's also the other, like the main thing is they multiply, don't add. So Q prime, if this was a vector, would be Q plus delta Q. Here it's Q times delta Q. And now we're going to Taylor expand this using the tricks. We're going to basically take a little phi in there, right? So we're going to get Q using the stuff from before, Q plus Q times like a phi hat, 1/2 phi hat, right? And if I kind of write this down using all this notation from before, this is Q plus L H 1/2 phi. It's the same stuff we just did. And now I'm going to say this is, we're going to do the other side. So we got X plus delta X, where that's a vector and that adds. This guy equals, this is normal stuff, df dx delta X. So sorry. That's cool. And now we're going to put it all together. So we've got, so we'll put the 1/2 up here, L H phi equals df dx times delta X. So now what I'm going to do is, remember, ultimately what I want is I want to get phi over here by itself. So I need to move all this stuff over to the right. In some sense, I want to invert this and move it over, right? I can't do that because, well, I can with this guy. That's actually easy. This guy's orthogonal. This guy's not square though. So, but we'll kind of write this real quick. We talked about this, I think, when we did this originally. This guy's orthogonal. So L transpose equals L inverse. That's kind of nice. So I can move that guy over. And I can move the factor of 2 over. So I end up with H phi equals 2 L of Q transpose partial F partial X delta X. And it turns out, I don't know, what's the right way to talk about this? Basically, you can also take this guy and move it over, and it turns. So this guy's taking this thing, which is 3D, and mapping it to a 4D thing with zeros on the top. Basically, I don't care about the top row of zeros. So what this guy's going to do is go over here and just hack off the row, top row, and give me the 3D thing. So this is a legal move, even though the dimensions are kind of funky. So then this guy this gives me this. Okay, and the punchline is, so then this guy is G transpose from before. And basically, on the input side, I had to multiply it by a 1/2. On the output side, I multiply by a 2. That sort of, these things show up, kind of annoying. But the gist of it is, on the output side, I just multiply by a V transpose. If I have a function that eats a quaternion and spits out a quaternion, and I do this on both sides, then the factor of 2 cancel out. It's cool. Otherwise, if I only go one way, then I end up with a factor of 2 I got to keep track of somewhere. Cool. So that's the end of this story. Whenever we want to whenever we're turning output, take the standard Jacobian and left multiply by G transpose. Okay, and then like the bottom line thing, I'll do this, I'll say this for next time. Essentially, what we're gonna do like is we're just gonna use this on the kinematics. This is gonna let us map from quaternion things. When we do the kinematic Jacobian step to get velocities, it's gonna give us omegas instead of quaternion derivatives, which are stupid and annoying and we don't want. And now when we have omegas, we can do our nice mass matrix stuff, and this generalizes. But we'll do this the next time because we're over time. The end. Thank you. Catch you next time. I'll hang out for a bit.